In the next few lectures, we're going to talk about the history of astronomy, how we got from ancient times to at least the 16 or 1700s. Later on in the semester, we'll talk more about modern astronomy, people like Einstein, things like relativity and black holes. We're going to get as far as Isaac Newton in our lectures now about history. I want to start out talking a little bit about ancient history, particularly something called archaeoastronomy. Archaeoastronomy is just about how ancient peoples were able to build amazing buildings or do amazing studies that related to astronomy. Perhaps the most famous example of archaeoastronomy is this one, Stonehenge, located in England. A few things that are important about Stonehenge. You'll notice right here, sort of away from the actual circle of stones, there is a single stone standing here. This stone is called the heel stone. It's quite tall, about 8 or 10 feet tall. Here I am a few years ago when I was visiting, so you can get an idea of the size. This is quite a tall stone. So what is special about this heel stone? Well, on the summer solstice, and only on the summer solstice, the sun rises directly over the heel stone. So if you were standing right in the middle of the stone circle, you would see the sun appear to rise right over that heel stone on the summer solstice. There are close to 100 different alignments within Stonehenge where things will line up with where the moon will rise on a certain day or where the sun will rise on a certain day. This structure, which was built almost 5,000 years ago, is an amazing calendar, an amazing way of marking the passing of the year by looking at where stars rise, stars set. A second archaeoastronomy object that's quite interesting is the Great Pyramid. This is about as old as Stonehenge, also about 5,000 years old. It was built, as you may know, as a tomb for the ancient pharaohs, the rulers of Egypt. What's interesting about the Great Pyramid, at least as far as astronomy goes, is inside the tomb, right near the burial chamber, there are 2 air shafts. One air shaft points out towards the star, or pointed at least out towards the star Thuban. Why was Thuban important? Well, if you think back to the lecture on precession about 5,000 years ago, what was special about Thuban? It happened to be the North Star then. So in some sense, they were lining up their burial chamber exactly north, exactly to that North Star. The other air shaft pointed to a star in Orion's belt. There actually are 3 pyramids, at least in the Great Pyramid area. Each one of those pyramids points to one of the 3 stars in Orion's belt. Why is that special? Well, for the ancient Egyptians, Orion was the god Osiris, the god of the afterlife. So in some sense, they were pointing their pharaoh, pointing their dead ruler towards the afterlife, towards Osiris. A little more closer to home and also a little more recent is Chichen Itza. This is built in about the 1100s. It's located in the Yucatan Peninsula of Mexico, and it's a Mayan ruin. This pyramid, which has 91 steps on each side, was built with a really interesting astronomy alignment. On the equinoxes, remember we talked about seasons, this is the beginning of spring and the beginning of fall. On the equinoxes, as the sun is setting over here to the west, you get a shadow that looks like a snake crawling down the side of the pyramid. This shadow only appears on the equinoxes. That's why there's always a bunch of people gathered around to watch when that event happens. And it was not an accident. This was built intentionally to create this shadow. The Mayans believe the snake actually lived in the temple, in the pyramid, and then twice a year would go down from the temple to go to a local sinkhole, local cenote, to eat the sacrifices that have been offered to it there. One final archaeoastronomy object, there are hundreds of these I could cover, but these are some of the more interesting ones, I think, is what's called the Newgrange Passage Tomb. This is in Ireland. It is actually the oldest of any of the ones we've talked about, over 5,000 years old. You'll notice sort of an entryway here. On the winter solstice, as the sun rises so it shines right down that entryway and lights up a central chamber located right in the middle of that passage tomb. So right in the middle over here. It only happens on the winter solstice, maybe a day before, a day after. This is not a coincidence. All of these objects here were clearly built to either mark the passage of time or as a way of showing respect to the stars, which for a lot of cultures they saw as deities, as gods. I want to move now to talking about sort of the development of astronomy as science, because none of what was going on that I showed you so far with the archaeoastronomy was really trying to understand why things were the way they were. Why was the sky the way it was? And that's really what astronomy science is about, trying to understand why. Some of the first, at least, records we have from the West of people trying to understand why things were the way they were came from the ancient Greeks. Two of these things I'll talk about now. The first one was by a guy I'm sure you've heard of by the name of Aristotle, very famous person from ancient Greek times. And he was one of the first, if not the first, to give evidence to show that the Earth is round. He did this over 2,000 years ago. Now you might think, wow, that's a big exciting discovery. Of course the Earth is round. But remember, what we experience in our daily life, we don't see the curvature of the Earth. The Earth doesn't necessarily seem round to us. Well, how did he go about this? He was aware of eclipses, and he said, okay, well, let's look. Look at the moon here during a lunar eclipse. Here we have a picture of it up here. Notice the red color, which is a good characteristic of a lunar eclipse. What are you seeing here? You're seeing the shadow of the Earth's umbra, falling on the moon. But notice something here. The shadow of the Earth's umbra, is curved. Aristotle said, well, if something is curved, has a curved shadow, that means it's probably curved as well. And that was how he argued and reasoned that the Earth must be round. Well, if the Earth is round, how big is it? And that was some work done by a guy named Eratosthenes, about 100 or so years after Aristotle. What he did was he noticed that on a certain day of the year, the sun passed directly overhead in one city. What he did is he had a friend who lived in a city a certain number of miles away measure how high the sun got in the sky on that same day. It wasn't directly overhead. It was about a 7-degree angle. But by noticing how high the sun got at his friend's city, and also by knowing how far apart the two cities were, he was able to estimate how far it was all the way around. And he estimated the diameter of the Earth was about 13,000 kilometers. How close was he to the right answer? Well, the actual answer is 12,800 kilometers, which I think is pretty good, considering this was work that was done thousands of years ago by someone who never left the area where he was born, never traveled more than a few hundred miles from the place that he was born. Now I want to try and talk a little bit about how the ancient Greeks and how people in the West saw our solar system. What's in the middle? What's happening in our solar system? What's happening in our universe? And to understand that, first, we have to talk a little bit about the planets and what the planets do. Well, one of the things that ancient Greeks knew immediately about the planets were they were different from stars. And the difference they saw between planets and stars was that planets moved compared to the background stars. If you notice where a planet was in the sky one day, the next day it would have moved a little bit compared to those constellations. And it keeps moving through the sky. This is the same as what we've seen before with the sun, how the sun moves through 13 constellations as it goes around the celestial sphere each year. That was how they figured out the difference between planets and stars. Planets moved compared to the background stars. At this point, the ancient Greeks knew about 5 planets. They could see Mercury and Venus. They could see Mars, Jupiter, and Saturn. The ones beyond that, Uranus and Neptune, you can only see with a telescope, so they were not aware of them. So how does this work? Well, for instance, here is the passage of Mars through the sky. So like on October 7th, you see Mars right over here. Here's where Mars would be on October 13th compared to all the stars, October 30th, and so forth. And notice what's happening. Mars is moving this way compared to the celestial sphere, but then after a while it will stop, turn back around, and go the opposite direction for a while. This is what we call retrograde motion, when the planet seems to be moving backwards compared to the celestial sphere. Now keep in mind, this is not a planet actually moving backwards in the sky. Planets still rise in the east, they still set in the west every day, nothing strange happening. But if you compare where a planet is one day compared to where it is the next day, there'll be a time when it seems like it's moving backwards compared to the stars in the celestial sphere. All planets do this. This is something that the ancient Greeks realized every planet did. And it was something that needed to be at least figured out when they tried to describe how the solar system worked. Well, the very first model of the solar system was created in about 400 BC, give or take, by a guy named Eudoxus. His idea was that the stars and planets are all mounted on these crystal spheres, one inside the other, almost like those sort of Russian nesting dolls where one doll is inside the other. Same kind of thing. And each of these planets, or the sun, or the moon, these spheres, they're on turn, and that causes the planets to go around the Earth. Now, an important thing to notice here, we're talking about the Earth in the middle. We now know this is not true, but the ancient Greeks believed the Earth was at the center of the universe. It's what we call a geocentric model. Geo means Earth. The Earth was in the middle. They believed that everything, including the sun, orbited the Earth. And this view was pretty much accepted as the correct view until about 1500 AD, about 500 years ago. Now, the problem with Eudoxus' model was he made no attempt to try and explain, for instance, how retrograde motion worked. He didn't try and match his observation. He didn't try and match his theory with actual observations. He didn't try and match it with what he saw in the sky. He just said, hey, this model with the crystal spheres, it sounds like a beautiful idea, so we're going to go with it. The first person to really try and match observations with what a theory would suggest was the Greek guy Ptolemy. He came around about 100 AD. He was still very much a geocentric model person. The Earth is definitely in the middle. But then he was trying to explain that retrograde motion, that backwards motion. And what he said was, all of the planets actually orbit on these things called epicycles. So Venus, say, for instance, is sitting on this thing here called an epicycle. And Venus goes around this epicycle as the epicycle itself goes around the Earth. So it's almost like a bicycle wheel spinning as the whole thing spins. This wheel spins, the planet goes around the epicycle while the epicycle goes around the Earth. And the interesting thing is, you can see in this diagram here, this actually can create retrograde motion. What you'll notice, if we start the animation here, you see the epicycle here and the planet going around the epicycle as the whole epicycle goes around the Earth. But you'll notice every once in a while, like coming up right here, when the planet's going one direction, the opposite direction on the epicycle compared to how the epicycle is going around the Earth, like right here, it looks like it goes backwards. You're able to get this retrograde motion. Ptolemy had an epicycle for every planet that was out there in the sky, since all the planets seemed to go through this retrograde motion. And with this, he created a model that, at least based on the observations they had at the time, accurately described what was going on in the sky. What we're going to see in the next lecture is, as scientists made better and better observations of where the planets were in the sky, where they were located, they began to realize that, what Ptolemy was saying, what the geocentric model was saying, what it was predicting for where planets would be in the sky, was not quite right. Maybe there needed to be a change to the theory, a different solution. That's what we call the heliocentric model, which is the accurate model of the solar system, and that'll be the subject of our next lecture.